A little bit more about ionic compounds and how we figure out what compounds exist and write their formulas. So, in general, and this applies to all chemical formulas, not just ionic ones, in writing a chemical formula to describe a compound, we use element symbols from the periodic table to indicate which elements are present. And we use subscripts, we use numerical subscripts to indicate how many. So we use element symbols and numeric subscripts to indicate how many atoms of which elements are present in a compound or molecule. And one thing that's really important to remember is that the subscript, the numbers, refer to the element before. So, for instance, H2O is a formula I know you're all familiar with. The 2 is referring to the hydrogen. So the subscript is always telling you how many atoms there are of the element before it. So H2O consists of 2 atoms of hydrogen and 1 atom of oxygen. In just another random example, C3H8, each subscript refers to the element listed immediately before it. So the 3 is for carbon, the 8 is for hydrogen. So this is a molecule that would contain 3 atoms of carbon, 8 atoms of hydrogen. So make sure you're always referencing the subscript to the correct element so you can keep track of how many atoms you have when you're drawing structures, which we'll get into later. So for ionic compounds specifically, so again, this previous information was for anything. For ionic compounds specifically, these are things that contain ionic bonds. And there are a few rules we need to follow in order for an ionic compound to be valid. Well, mostly just one rule, actually. So ionic compounds are things that contain ionic bonds, or substances that contain ionic bonds, which usually means there's one metal and one nonmetal. So in these compounds, the metal will be our cation, will be the positively charged ion, and the nonmetal, the nonmetal will be our anion, or a negatively charged ion. So we will, for the purposes of this course, only have one type of each in a given compound. More complex compounds do exist, but for now we're just going to deal with compounds that contain one kind of cation and one kind of anion, not multiple of either. So for a given combination of ions, there is only one way that you can actually combine them for ionic compounds. There is only one valid combination. So a given combination of cation and anion can only combine in one way. So the reason for that is that we know, I need to move this down, we know that ions have charges. That's what makes an ion an ion. But an ionic compound, an ionic compound must have an overall charge of 0. So the charge on our compound as a whole must add to 0. So if you have a cation with a positive 1 charge and an anion with a negative 1 charge, the only way that they can combine is in a 1-to-1 ratio. For every cation, you need 1 anion. If your charges are different, that ratio is going to change. So we're going to need to know what the charges on our ions are. But thankfully, we can predict that from the periodic table. So we always need to know what the charge is. That's always something you need to be aware of on your cation and your anion. But we can predict it from the periodic table. So just by looking at what family something is in, we're actually going to be able to predict what charge it has. So the families are the columns on the periodic table. So each family or each area here is going to have somewhat different properties in terms of its charge. So this middle section, the transition metals, are weird, but they all kind of get lumped together. For right now, we are going to completely ignore the lanthanides and actinides. We won't deal with them in ionic compounds. They're really, really uncommon anyways, so we're just not going to worry about it. Most of them all tend to form +3 ions, but that's not really that important. Sorry. Oops. Wrong writing utensil. So, I'll explain what I'm doing here in a moment. I'm sorry, I keep screwing this up. I'm running out of colors. Alrighty. So, each family kind of has its own characteristic charge here. And the charges that our ions like to form are the ones that generally make them isoelectronic to a noble gas. So, for the first family here, lithium, sodium, potassium, we call those the alkali metals. In order to become isoelectronic with a noble gas, they need to lose 1 electron. They all have 1 valence electron as a neutral atom. If they lose that, they look like a noble gas. So for instance, sodium has 1 electron in its 3s shell. If it loses that 1 electron, it now has the same electron configuration as neon. So everything in this family, for that reason, likes to form +1 ions. The one sort of exception here is hydrogen, which can form either +1 or -1. Because if it forms a +1, it has no electrons left, so that's fine. It has completely empty shells. If it forms a -1 ion, Now it goes from having 1 electron in its valence shell to having 2 electrons, which for hydrogen is going to be the same as helium. So that one's a bit of an exception. The negative charge is still pretty rare. It still prefers +1 most of the time, but it does also form -1 fairly regularly. So similar idea here. The next family tends to form +2 because these ones will lose 2 valence electrons, will give them the same configuration as a noble gas. For instance, beryllium has 2 electrons in its 2s. If it loses 1 and then 2, now it has the same configuration as helium. We're going to skip over that group in the middle for right now and come over to the boron group, which generally forms ions of +3. You can see the trend here. We're mostly concerned with the arrangement in the S and P subshells, so skipping over the D block for now. You may expect the next ones to go to +4, and you're not entirely wrong, but you'll notice that I shaded this column in 2 different colors. Anything that I shaded in this dark gray generally does not form ions. Charges larger than +3 are not common, just because the charge is so large that it tends not to be very stable. But these 2 down here are large enough atoms that they do often form charges of either +2 or +4. So these ones are a little bit weird. They can do 2 different things. And then continuing on to the next family, these guys are now going to go in the other direction. It's easier for them to gain electrons than lose to become like a noble gas. If nitrogen wanted to lose electrons to become like a noble gas, it would have to lose 5. If we're starting here and losing electrons, we'd have to lose 1, 2, 3, 4, 5 before we find helium. Or we can gain 1, 2, 3 and become like neon. So this is where we're going to start forming anions instead. So nitrogen and all of the things in its family tend to form ions of -3. Oxygen and everything in its family tends to form ions of -2. And fluorine and the rest of the halogen family tend to form ions of -1. So just by looking at where something is on the periodic table, for the most part, we can predict its ions. The one exception is this area in the middle. So these are known as our transition metals. And most of them will form more than one possible charge. So these are the ones that we really can't predict what the charge is going to be. Without some additional information. So if we have the formula, we can figure out the charge, but we can't just figure out the formula without some other pieces of information. So most of these can form multiple different charges. For instance, iron can be either +2 or +3. Copper can be +1 or +2. Chromium can be anything from +1 to +6, I think. So some of these have a lot of options. A few of them do only form 1 regularly. Silver's pretty much always +1. Zinc's pretty much always +2. So a few you can predict, but not very many. So for these, we usually need a little bit more information to figure out what's going on. And we'll talk about how we do that in the days to come. So for ions involving a single atom, we can predict their charges just by looking at the periodic table. There are also what we refer to as polyatomic ions, which are just ions containing more than one atom. So they're a group of atoms that together have a charge. So a group of atoms that have a charge all together. So there's a list of some of the more common ones to the right. You don't need to memorize this or anything. But what this essentially is showing you is that this group of atoms together, C2H3O2, collectively has a -1 charge. So that whole thing is functioning as one unit with a -1 charge overall. So a lot of ionic compounds and use these polyatomic ions, so you'll want to keep a list handy. I will post a list along with this. Because you always need to be aware of the charge. You'll notice that a lot of them are -1 is pretty common. Actually, that one's -2, sorry. -1 is pretty common to a lot of them, but some of them are -2. And sometimes they're even -3. We do have one positively charged ion on here as well. Most polyatomics tend to be anions. So what all of this allows us to do is write the formula for an ionic compound if we know what ions are involved. So we're going to do a few examples. And remember that our goal is that our charge must add to 0. So we're going to be using subscripts to adjust the ratio and make that true. So, first example is sodium and bromine. So we're looking for what would the formula of the compound be when an ion of sodium and an ion of bromine bond ionically to one another. So we're going to want to reference our periodic table. So sodium is over here in the leftmost family, which likes to form charges of +1. Bromine is over here, likes to form charges of -1. So looking at this first example, sodium will generally have a +1 charge, bromine will generally have a -1 charge. So when those two things combine, they have to do so in a 1-to-1 ratio. So when those two elements combine in an ionic compound, NaBr is the formula that you will get. For every 1 sodium ion, there is 1 bromine ion, because +1 plus -1 equals 0 without us having to change anything at all. The next example, potassium and oxygen. Potassium is once again in that same family that forms +1 ions, but oxygen is -2. So when we come back and look at this, we have +1 for our cation, -2 for our anion. So these ones don't automatically balance each other out. We have 2 negatives and only 1 positive, so we're going to need 2 potassium ions for every 1 oxygen. So we'll use a subscript after potassium to indicate that. So we need 2 potassium for every oxygen in order to balance charge. So that's always what we're looking to do, is figure out how do we get the total charge on this to add to 0. So why don't you pause the video here, take a few minutes, and try to do these next 3 examples: aluminum and chlorine, calcium and acetate, and lithium and carbonate. Note that acetate and carbonate are going to come from your polyatomic ions list. So acetate's here, and carbonate is just a couple rows below it. So you'll want to use the periodic table for the individual elements and just look for the charge on the polyatomic ions list for those ones. Oh, there's another one down the bottom there, barium and phosphate too. So take a few minutes, try and do those, and then I'll walk through them with you. All right, so you should have found from your periodic table that aluminum likes to have a +3 charge, Chlorine likes to have -1 based on the families that they're in. So this means that we're going to need 3 chlorine atoms for every 1 aluminum. So the formula for the compound that forms between those two will be AlCl3. That gives us 3 negative charges, 1 from each of our 3 chlorines, and 3 positive charges are all on aluminum. So calcium acetate, calcium likes to be +2. Acetate has a charge of -1. So this one you might have run into some problems trying to do on your own of how do I actually symbolize this. We need 2 acetates for every 1 calcium in order for the charge to balance out. But polyatomic ions are special in that this arrangement of 2 carbons, 3 hydrogens, and 2 oxygens, in the case of acetate, is functioning like one particle, is functioning like one thing. That in and of itself is a special unit. That's why it has a special name. So we actually don't just want to double all of those subscripts. We don't want to mess with the acetate formula. So instead of doubling each of those subscripts to indicate that we have 2 acetate ions, we actually use parentheses and put another subscript after it. So we use parentheses around polyatomic ions. When we have more than 1 in the formula. If there's only 1, you don't need parentheses, but if you need a subscript after, you need the parentheses to be there. So in this case, the 2 is referring to everything inside. So your parentheses, just like in math, refer to make a group or a grouping symbol. So having a subscript immediately after the parentheses means that there's 2 of everything that's inside. So there are a grand total of 4 carbon atoms, 6 hydrogen atoms, and 4 oxygen atoms, but we write it this way to signify that it's functioning as 2 acetate ions, that they are 2 separate particles still. So next up was lithium carbonate. So lithium is in the first column, so it generally has a +1 charge. Carbonate is one of the polyatomics, is -2. So we have 2 negatives, 1 positive, means we're going to need twice as many lithium as carbonates. The formula for carbonate is CO3. And then last but not least, barium is in the second column, so it will have a +2 charge. Phosphate is a polyatomic ion with a -3 charge. So in order to balance our charges out, you can't have half an atom. We can't use fractions as our subscripts. So we're going to need to end up with 3 barium and 2 phosphate. And again, we'll need to use the parentheses around phosphate to indicate that there's more than one of those. So this gives us 3 times +2 is +6. 2 times -3 is -6. So in this formula, we have a grand total of 6 positive charges, 6 negative charges that balance one another out to 0.